second derivative for local extrema. If f prime of c is equal to 0, that means c is a critical number, and f prime of c is equal to 0. And your second derivative is greater than 0. That implies that f of c is a local minimum. Because if you have f prime of f double prime at c greater than 0, that means the graph is concave upward. And at this point here, which is a critical number, that is f prime of c is equal to 0, and you have concave upward there, this point here is a local minimum. And also, if the second derivative is less than 0 at x equals c, then you have a local maximum at x equals c. This next theorem here will use the second derivative test to find for absolute extrema on an interval. Suppose you have a continuous function in an interval I from a to b with only one critical number c on that open interval ab. If f prime of c is equal to 0, that means c is a critical number. The first derivative at x equals c is equal to 0. And the value of the second derivative evaluated at x equals c is positive, then f of c is the absolute minimum on this interval here. And also, if f prime of c is equal to 0, that is a critical number, x equals c is a critical number, and the value of the second derivative at x equals c is negative, it's less than 0, then f of c is the absolute maximum on an interval I. Now, this one illustrates the theorem here. Again, the x is a 0 of the first derivative, and if the value of the second derivative is positive, that means the graph of the function is concave upward. So therefore, at the point here where f prime of c is equal to 0 is a local minimum. Now, if the value of the second derivative at x equals c, where c is a 0 of the first derivative, is negative, the graph is concave downward. That means at the critical number c, f of c is a local maximum. And lastly, if f of double prime at c is 0, then the test does not apply. To illustrate, we consider the example here to find the absolute extrema of this function on the open interval 0 to positive infinity. As a first step, we will find the critical number for the function here, and we do that by differentiating the function f of x with respect to x. Now, before we differentiate f of x, we will first rewrite f of x as x plus 4. Now, we rewrite 4 over x as 4 times 1 over x. Now, 1 over x can be rewritten using the formula here. So if you recall, 1 over x to the n is equal to x to the negative n. So that means this 1 over x here can be written as x to the negative 1. Now after that, we're now ready to differentiate our function. The derivative of x is equal to 1, and the derivative of this expression here is 4. So constant multiple property, copy 4, and then differentiate x to the negative 1. The derivative of that is -1 times x to the -2, because you subtract 1 from -1. -1 minus 1 is -2. So this is now the derivative of this expression here. Now, so that's a derivative. So since we want to get the 0 of the derivative here, then we will have to simplify this. So this is 1, and then the second term now becomes -4 because of the -1 here. And now remember, if you have a negative exponent, x to the -n is equal to 1 over x to the n. So this x to the -2 here will be 1 over x squared. Then this is just equal to 1 minus 4 over x squared. Then we combine this. We can write 1 as x squared over x squared. So therefore we have, if you write 1 as x squared over x squared, we can then write this as a single fraction. You have x squared minus 4. That is your f prime of x. Now, if you want the values of x such that f prime of x is equal to 0, that means x squared minus 4 over x squared is 0. Now, if you have a fraction and that's equal to 0, that implies that the numerator is equal to 0. So this means that x squared minus 4 is equal to 0. And then you compute for x. So you have x squared is equal to 4, and that x here is equal to plus or minus 2. So you have two values of x here that will make your first derivative equal to 0. Then you go back and check your interval. Which of the two values of x here is on this interval here? We only have x is equal to 2. X is equal to 2 is on the interval 0 to infinity. And then the next step is to plug in this value of x here to the second derivative of our function. So now let's go ahead and find the second derivative of our function. So f double prime of x is equal to, now you differentiate this, this is your first derivative here. Let me copy that first. F prime of x is equal to 1, and then you have minus, so the negative here becomes minus, so minus 4x to the -2. And then second derivative is equal to, now the derivative of 1 is 0, minus, and then copy 4, and then you differentiate x to the -2. The derivative of that is -2, you bring down -2, times x to the, and then you subtract 1 from -2, -3. Now that's your second derivative. And this is just equal to, you know, -4 times -2 is positive 8, x to the -3. And this is equal to 8 over x cubed. So this is your second derivative. Now we want to plug in 2 to the second derivative. So let's evaluate the second derivative at x equals 2. So you have 8 over, and then replace x here by 2. So 2 cubed. Now 2 cubed is equal to 8. So you have 8 over 8. And that is equal to 1, which is greater than 0. So again, if it is greater than 0 using the second derivative test, that means the graph there is concave upward. If it is concave upward, we have a local minimum. And in this case, since we only have one value using the theorem, that local minimum is actually the absolute minimum.